the subject of these first couple of papers with Francesco Aprile, James Drummond, and Hynek Paul, who's in the audience. He's kind of my name jewel. Okay, so the outline is as follows. I'm going to start talking about ADS CFT, n equals 4 Yang-Mills. I think in this audience I can skip over this quite quickly. The spectrum, which is of course a key aspect of this whole story. The spectrum at strong coupling, and then the correlators. And I'll try and convey the basic idea, and then I'll go into the details. Details, first of all, being superblocks, unmixing of different operators of the same quantum numbers. And then we'll, along the way, get a lot of data, a lot of anomalous dimensions and three-point functions, which aren't strictly needed in order to calculate the 222 1 over n to the 4th correlation function, but they're a very nice byproduct. So I'll then discuss the results, all this data, look at the one-loop correlation function. So that, hopefully, will be the first half of the talk, although I expect it may take longer than that. And then I'll discuss the more recent work, which is in progress, and has been in progress for quite a long time, in fact. But I ambitiously put an 04 there, but we'll see. So that should hopefully be coming out quite soon. On higher charge correlators, and I'll basically, I won't. Well, I'll give you a few details, but I'll basically try and convey how to do it, what the new features that you get when you go beyond 2222. And then there's this new kind of intriguing thing, which is sort of we call generalized tree amplitudes that turn out to be useful for this. Okay, so you've all seen a slide like this at some point. This is ADS CFT. We're looking at the quantum gravity limit, so we're taking alpha string corrections to 0, and the TIFF coupling to infinity, and then the 1 over n expansion we think of as a quantum gravity loop expansion. So you've got the free disconnected from the Yang-Mills point of view parts are the leading corrections, and you've got 1 over n squared times the supergravity tree level amplitudes. And we want to basically use data from here to induce 1 over n to the 4th, i.e. one loop gravity. So again, from the correlation function side, we're looking at the strong Tufte coupling limit expanding in 1 over n squared, and we want to find the 1 over n to the 4th term. Okay, I can use this, can't I? So this is a kind of a sketch. I'll come back to this a bit later and add a few more data points. So it's not supposed to have too much meaning. I'm just trying to put in the parameters where different things occur. So here I've got G Newton in 10 dimensions, which is 1 over n squared. So tree level supergravity, I normalize everything, so we start with 1 here. So this is a 1 over n squared correction times alpha prime to the 0. Of course, there are then, you can look at tree level stringy corrections, and many people here have done so. Or you can go further in this direction, and you can look at loop level supergravity corrections. And then, of course, there are things up here which people have also looked at recently. Okay, so now again, the main advantage of this strong coupling expansion over, for example, trying to do super Yang-Mills at weak coupling is the spectrum is so much simplified. It's vastly simplified. And that's, of course, you know from string theory, because we're basically going from string theory to supergravity. So all the massive string states are suppressed, and only supergravity states remain. So on the n equals 4 super Yang-Mills side, the only remaining operators are these operators, O2 and ON, that we've already seen before, which trace of phi squared, trace of phi to the n. Actually, there's 1 over n corrections to the definition of the single particle operator, which do become important when you're looking at higher charge correlators. So this corresponds to the graviton multiplet. This corresponds to higher Kaluza-Klein modes of the graviton multiplet. So there, if you like, you can think of them almost as your fundamental fields, if you like. And then all other operators that remain are simply products of these. So you don't need to really worry about the trace structure, SUN, all that sort of stuff. You're just taking products of ON. So in particular, 2-particle states. Of course, you can have different scale. There are 6 scalars. I'll go into that shortly. So there's an SU4 structure here. And then you can have derivatives inside here. Derivatives d to the L symmetrized, or you can have a Laplacian, a box to the n. There can be double trace or triple trace, but then actually at the order that we're considering so far, the triple trace are also suppressed. So in actual fact, it's even simpler. You can just consider double trace operators, products of the ONs. So this is a point which doesn't. Well, I mean, it's important to get the details right. It won't really come up again in this talk. Is that you have to get the correct definition of a single particle operator, and I think this comes back to the point in the last talk when you were talking about P1 plus P2 and the 3-point function. So a way of thinking about that is actually the single particle operator is not trace phi to the 4, but it is this particular combination. And if you take this combination is defined for us to be the combination which is orthogonal to the double trace phi squared, trace phi squared. So, and in some sense, that's why that 3-point function you were discussing vanishes, just because I've defined it that way. But this is a good way of thinking about the spectrum, actually, which I think, although people have come across this, I think maybe this way of thinking about it can be developed quite a bit more. Right, sorry, yeah. It is, but you need to, it is, but with this guy fixed. Right, you can once you've diagonalized it, I can then rotate it orthogonally, and they're still orthogonal, right? So you have to make a choice. Right, so there are many bases. There's this Schur polynomial basis of Corley, Ramgul, and people. They have orthogonal 2-point functions in the UN theory, by the way, which should be just rotated versions of these. But we're making a stronger statement. We're somehow saying that a single particle operator should be defined to be orthogonal to all higher trace particles. So this guy, we say, is somehow special. Trace phi squared should stay as it is. I'm not sure. You mean which Hamiltonian are you talking about? I mean, these are all half BPS operators here. I mean, sorry, I understand what you're saying. Yeah, now these are all half BPS. You can't get anything from looking at anomalous dimensions or anything like that. So maybe it is, but it's trivially so. Any combination would be, I think. Yeah. Yes. No, this choice gives results that are consistent with supergravity results. And it's precisely related to this point you made about the 3-point function in the last talk. There's a certain 3-point function that vanishes. So OP1, OP2 with an operator of dimension P1 plus P2 has to vanish, and you can rephrase that in this way. Yeah, everything's half BPS then. No. Not yet, no. So I'm just defining for you what I mean by a single particle half BPS operator. And this is just an example, but this definition, that definition is a complete definition. Yeah, I want this to be exact in n. And in fact, if you use this definition, I believe it correctly interpolates between so-called giant graviton states and single particle states, which is something that hasn't been seen before. Okay, okay, very good. So, in fact, it doesn't matter if you include here the statement that they have to be orthogonal to trace phi. If you're doing UN, then you can have an object at trace phi. And if you also say this has to be orthogonal to those, or any products of trace phi, then you get exactly the same operators for SUN and for UN. Okay. So there's lots of details like this that you have to kind of get right when you're looking at these higher charge correlators. So now let me go back to the basic idea. So again, many of you, I think, will know and understand this immediately at this level. The basic idea is just to take the OPE and plug it into a 4-point function, so you get something like this, where I want to look at the u to the power of a anomalous dimension. And then if you expand this, so I expand this in the coupling. The coupling is 1 over n squared here. So the first term is just the u to the anomalous dimension disappears, and I get the 3-point function squared. And next order in 1 over n squared, then I bring down from here, I bring down a log u. So I get 3-point function squared times log u times the anomalous dimension times the block. And then at the next order, you get this so-called double discontinuity, where I have a log squared u from just doing the same thing again, bringing down 2 powers from here. Of course, you get other terms as well from doing other points, but the only term that goes like logs, that has a log squared u, is c squared times eta squared. And so the main point here is that if you know these two terms, then you might think, if you're very naive, I can just extract this term. Okay, so that's the sort of rough idea, and that would be the case if there wasn't this sum over operators. If there was only one operator here, then I could take this, I could take this, I could divide them, that would give me eta and c squared separately, and then I could plug them into here and get the answer. Now the reason it's not as simple as that is because there's more than one operator with the same naive quantum numbers. Okay, well, that was the end of the gentle introduction. So this is the gentle introduction. That's the basic idea as to how this all works, and I guess all of you know that part anyway, probably. Now I go into some technical details. So the first technical detail, of course, there's more than one scalar in the game. There are 6 scalars, and so we use an auxiliary variable, which I call yi, and Zenon, this is your ti. And then my scalar then becomes a function of x and y, a sort of trivial function of y, if you like. It's just phi I, yi. But we get a y for each scalar now. In fact, this really is, or can be thought of as, in a bigger formalism called analytic superspace. But in actual fact, you don't need the full machinery to deal with the 4-point function. You just need a few aspects. So we sort of suppress this. Okay, the second problem, I referred to blocks, but of course we really need superblocks. That removes some sort of trivial degeneracy to do with the multiplet structure. So I'll talk a little bit about superblocks on the next couple of slides, very quickly. That enables you then to, over here, this is a sum over primaries, that now will become a sum over superprimaries, if these are superblocks instead of blocks. Okay, so you've dealt with a lot of degeneracy by using superblocks. But there's still some degeneracy left, as I'll explain. You still get multiplets with the same quantum numbers. And so then you come to the second part, the solution to that, which is to use many different correlators of higher charges, P, P, Q, Q. Okay. So let me write down a full supercorrelator. So we've got x variables 1, 2, 3, and 4 for our 4 points, and we've got y variables 4 points as well. And the 2, 2, 2, 2 correlation function up to order 1 over n squared looks like this. Okay, so the g's are superpropagators, so they're just yi.yj over xij squared. And so here you see essentially a free theory. These diagrams are corresponding to these, and these diagrams corresponding to these. So this is this free theory plus an interacting piece we saw previously. The precise interacting piece here is these 4 factors we saw before. I think they were written something like z minus 1 over alpha instead of x minus y, but this is essentially the same as what we saw in the last talk. And then the specific correction, which is computed using ADS calculations. So there's a lot of information on this slide. This is the precise 2, 2, 2, 2 correlator to order 1 over n squared. We want to try and find the next term, 1 over n to the 4th. But the structure here is also important. So the structure, as we saw, is free theory plus this factor times a function. And that's just a consequence of superconformal ward identities. And that's true for higher charge correlation functions as well, written in that form. Okay, this d bar 2422 we already saw. It's essentially a derivative of a box function. And as we also already saw, it has the form of weight 2 polylogs, in particular this block-Wigner dialog, essentially the box function, times a polynomial, plus weight 1 polylogs, i.e. log u and log v, times polynomials, plus polynomials, divided by x minus x bar to some power. So that's the structure, and this structure is kind of crucial. This sort of structure is going to generalize to our loop level. It's the same. You get the same structure as we've just seen for all tree level correlation functions, and we get a similar structure, but just increasing the weight for the loop level as well. Okay, good. So this is a key point. It's not. It's well, okay. The easiest way to is to look at the box function. The box function has x minus x bar in the denominator, just 1 power, and it's anti-symmetric in the numerator, so it's not really a singularity. And now I differentiate it. Each time I differentiate it with respect to u, I end up getting 2 more powers actually, because well, 1 power from differentiating it, but there's secretly a 1 over x minus x bar in the definition of du as well. So you get 2 powers. So here I'm hitting it with 3 derivatives, so that gives me 6 more powers. But you secretly know, of course, that it's not a natural singularity. So that puts a big constraint on the on this term. The numerator has to have 7 zeros as x equals x bar. I don't know if that answers your question. I mean, why? I mean, another answer is it is. But the key point is not really a singularity. Okay, that's okay, yeah, maybe that's an answer to the question. Okay, so the superblocks, very quickly, they're actually very straightforward for long operators. They have the same structure times a bosonic block times an internal block. So if you're just interested in analyzing this part, then all you have to do is take this and decompose it into ordinary bosonic blocks. The free theory, however, is more complicated. Now the superblocks are known. Now my favorite, not all my collaborators do this, I don't think, but my favored approach to dealing with the free theory and the protected sector is to uplift as follows. So very quickly, these blocks, you can lift the whole story of superblocks to an SU_m/2n theory instead of an SU2,2/4 theory. And in the free theory in particular, you can lift, so all the terms in the free theory are combinations of propagators, which in terms of the eigenvalue of, this is kind of like a cross ratio matrix, where this is x bar, y and y bar. And the terms that appear in the free theory I can think of as superdeterminants to a certain power of 1 minus this z. Anyway, I mean, there's a story behind this, but the whole thing can be then uplifted to any SU_m/2n theory in this form, and in fact, you can then actually go down to just SU_m. In that case, your Z just becomes an m by m matrix with eigenvalues x1 to xm. So this is the analog. If m equals 2, this would be your bosonic x and x bar variables. It kind of extends. Sorry? Where? This is a comma. Very good question. Yeah, this is a comma. So we have SU_m/2n. That's a slash. So it's a 2m/2n matrix. But then I reduce it down to a US m, 2m if you like. But the main point is that the blocks themselves in this theory are very simple. They're just natural determinants of the hypergeometric. So if you know bosonic blocks in 4 dimensions, you might sort of you might see this as a 2 by 2 determinant. It has the function. It's hypergeometric times hypergeometric minus hypergeometric times hypergeometric. It's actually naturally a 2 by 2 determinant. And then on the bottom you have x minus x bar, which is also a determinant, and that just generalizes to m by m. Anyway, these formulae are very straightforward, just to input, and then you can just analyze your free theory straightforwardly like that. Okay, good. So they're the blocks. So we've got the blocks, and now we can extract conformal partial wave coefficients from them. So in particular, we can extract C22O squared, and we can extract C22O squared e to O. But of course, we only get the sum over operators with the same quantum numbers. So let's have a look at what these operators are that have the same quantum numbers. And we're going to build it up in twist. So let's start with twist 4. Twist being dimension minus the spin. Okay, so twist 4, in fact, there is only one operator. So twist 4, we're happy. The only operator I can write down, the only long multiple I can write down is O2, d mu to the L O2, and here the SU4 is contracted. So it's a singlet. So there's only one operator, and now the naive thing works. I extract my block from the free theory, 2222 free theory. I get this. I extract it from the supergravity theory. I get that. If you like, I can divide them and get an anomalous dimension. This was done many years ago by Dolan and Osborne. Okay, now at twist 6, we start getting some complications. Here there are two operators. I mean, it's easy to see. I can have O3 times O3, that's twist 6. Or I can have O2, Laplacian O2. Laplacian has twist 2. So what do I get from the 222 correlator? I get two equations from free theory. Sorry, I get one equation from free theory, one equation from tree level, but I have four unknowns, namely the two OPE coefficients for the two operators and the two anomalous dimensions. So So we need more information. But that extra information comes naturally from looking at 2233 and 3333 correlators. Then we get 6 equations for 6 unknowns. Because, of course, we get 2 extra unknowns, the 3 OPEs, coefficients, but we've got extra equations. So you end up with 6 equations, 6 unknowns. It's a perfect system with a unique solution. Well, unique up to signs because of the square roots. And this is the solution. So, and now this is, I guess, a key point in hindsight is that these etas are rational. And they needn't be, because we're solving a quadratic equation to get them. So it's quite remarkable that the etas are rational. The c's also are square roots of rationals. Okay, but this then illustrates the main story of what we can do. We can now get essentially all the data we need by looking at lots of different correlation functions and manipulating the matrices. So maybe I'll quickly flash through this. This is the general story. At the moment, I'm just interested in singlet operators because they're the only ones that occur in the 2222 correlator. These are them all, so they're just OI plus 1, OA plus 1 contracted with Laplacians and derivatives. They all mix together. They all have the same twist. So you write down a matrix of 3-point functions. This matrix has to satisfy CC transpose equals A hat, which is the matrix of block coefficients of different correlation functions. So this is, if you like, your input. You extract this by doing a block a decomposition of all these correlation functions, and you get A hat. That's at free theory, then n to the 0. Then you do the same thing at 1 over n squared, tree level, using, of course, a key input for us was these results of Zenon and Rastelli. So they enable us to have all of these results here, and we could therefore extract this data. So then we have m hat as well. And you see that, again, we have the same number of unknowns as equations. So on this side, we have the matrix of 3-point functions plus eta, a total of t minus 1t unknowns. And the inputs are the equations, which are symmetric, but there's 2 of them, and you again get t minus 1t. So you can solve it. And, well, okay, I won't go into too many details, but it is nice to look at these 3-point functions, I think. There's a nice feature that you can reduce the 3-point function matrix to an orthonormal matrix, and that's because the free theory is naturally diagonal. Because because you're looking at the disconnected terms, and only the diagonal pieces of the matrix contribute here. So these ones where they're identical, they're the only ones that contribute at 1 over n to the 0. So you can factor that out, and you can phrase this 3-point functions as orthonormal matrices. So at twist 4, it's just 1, as it has to be. It's the only orthonormal 1-by-1 matrix we have. Here we get a 2-by-2 orthonormal matrix, so you can check in your head that the square of that plus square of that is 1, and they're orthogonal to each other. At twist 8 we get the following, and then at twist 10, and well, you can go further. But there's a sort of remarkable structure here. I mean, when you play with this, it's kind of remarkable that they end up being orthonormal, and it feels like they should exist in the maths literature somewhere or somehow. They're just orthonormal matrices of a variable that's sort of mostly linear in the variable under the square root. In actual fact, they do, as you get closer to the center of the matrix, you do start getting higher powers of L. Okay, anyway, there's an interesting story there, I think, that there's still probably more to say. But in the end, for what we need, we can now extract anomalous dimensions, and quickly, when you've done a few of them, you can find a formula for them. This is for any twist and any spin in the singlet sector, where I is enumerating the different operators with the same quantum numbers. So they're the anomalous dimensions, and then the OPE coefficients, they satisfy this complicated-looking structure, but it's basically just looking. You look at the structure of these matrices, and try and figure out the structure, and basically I allow for the 7/6. I just call that an unfixed coefficient. 5/3 unfixed coefficient. As you get closer to the middle of the matrix, you end up having unfixed polynomials in L. Anyway, that's all this is saying, where this is the unfixed polynomial. And then you impose that this matrix is orthonormal, and that fixes all these unfixed coefficients for you, just insisting with this structure on orthonormality. Okay, and then you can get an analytic formula for the 3-point functions that we actually need. Of course, there's far more 3-point functions here than we actually need for the 2-2-2-2 case. Okay. So, but all the story for the last 5 or 10 minutes has been talking about extracting this data, the 3-point function data and the anomalous dimension data, by taking a lot of correlation functions. And by because there's this nice structure, I mean, this was important for the way we were doing it, although, it may be not essential to do it this way. You could get a computer to try and do it all for you without, at each stage, getting analytic formulae. But now we have this data analytically. That means that you can do this sum to very high orders, of course, because you have full analytic control over the ingredients. Okay, and this is giving you now the full correlation function at 1/n to the 4th at the log squared u piece, the so-called double discontinuity, as a sum. But given that we have this fully analytically, you can perform the sum to high order and match to a plausible ansatz. And the ansatz we matched to was very similar to the one we've just seen for the d-bars. Polynomial times weight 2 polylogs plus similar things with lower weight polylogs divided by x minus x bar to some power. Okay, and then you can find the values of all of these things. Okay, well there's the full answer, and there's the polynomial. So this is the double discontinuity, and once you've found the double discontinuity, you then want to try and get the full function itself. And again, we simply wrote an ansatz down, a natural-looking ansatz given the tree-level structure and the double discontinuity structure. So again, we've got this x minus x bar to the 15 in the double discontinuity, so let's stick with that. We've got, obviously all this is multiplied by log squared u, so we've got log squared u times weight 2 polylogs and so on. So let's call that, let's call that a weight 4 polylog. Actually, they are single-valued harmonic polylogs. So single-valued harmonic polylog, weight 4, weight 3, weight 2, and so on and so forth, all multiplied by polynomials. They have a degree which is fixed by the power here because of crossing, which is x goes to 1/x. So if you had too high a degree here, you'd start introducing poles that you don't want when you do the crossing. Okay, so then we impose crossing symmetry. We impose that it's finite, as we just discussed, as x goes to x bar. And we, of course, impose that the log squared u matches what it has to. And in fact, within that ansatz, there's just one free parameter left over. So everything is fixed up to one free parameter. All the polynomials are fixed. The free parameter, after the fact, can be understood. So this is the ambiguity. And it's precisely a d bar 4444, which people have had known previously is a direct consequence of the r to the 4 term in the string theory effective action. So it's both a tree-level alpha prime queued correction, but also a one-loop supergravity counter term. The two are related. In fact, they're related by SL2Z of string theory. Okay, very good. So, but the main point is that we obtain the full one loop 2222 4-point amplitude. Again, going back to this diagram, that this is the this would be the tree level string theory correction, r to the 4, and then there's higher derivative corrections. I mean, people, I know that this has been discussed in previous talks. I guess these sorts of corrections. Now, here I'm thinking in a supergravity sense, where 1 over n squared and so g Newton and alpha prime are my parameters here. But in a string theory sense, maybe one would think instead of g string and alpha prime. And there you see that. So we're trying to compute. Well, we have computed this one loop amplitude. The ambiguity is the same function that sits here as a counter. From a supergravity point of view, it's a counter term. So it goes like gn squared divided by some quadratic length scale, some length scale squared. In string theory, this is gn squared over alpha prime, and it's directly related by SL2z to the other correction. So the point is, this is alpha prime to the 7 times g string squared. This is also is alpha prime to the 7 times a different pair of g strings. So these sit on the same alpha prime to the 7, but with different pairs of g string. Okay. So as we've seen, there's a lot of data that we found along the way. Not all of it was needed for the actual calculation, but we then thought, well, let's try and find more data. In fact, since we found all singlet anomalous dimensions, let's try and look at all double trace anomalous dimensions. So in order to do this, you need to look at different block expansions of different correlators. I won't go into the details, but the output quickly emerges a nice pattern, which is, well, first of all, you need to, of course, understand what the operators are. So it's an arbitrary operator in the SU4 ABA, spin L, twist tau, but there's actually a kind of a 2-parameter space of them now, because OP and OQ can vary. All these operators for P and Q satisfying this have the same quantum numbers. They fit in PQ space. They fit into a sort of rectangle. And the anomalous dimensions they have take this form. And in particular, they're degenerate, so this formula is independent of Q. So that's why I have these sort of vertical lines here. So all these operators have the same anomalous dimension at order 1 over n squared. Okay, and of course, this is now explained in terms of this 10D conformal symmetry we've just been hearing about. So the point there is that in 10 dimensions, there's really only one operator for each spin. And all these operators somehow come down from a single operator for each spin. Okay, so that's the story for the 2222 correlators. I want to now try and quickly sort of summarize some of the subtleties that appear when you look at higher charge correlators at one loop. So this, if you like, is we're trying to give an algorithm for how to compute arbitrary one loop 4-point functions of Kaluza-Klein gravity operators. Okay, so we're looking at PQRS. So there's a lot of new subtleties that appear here that weren't there in the 2222 case. So the first problem is this degeneracy I just mentioned, although that doesn't take place until you get to quite high charge. But at some point, I can't follow the same program that I've been doing and getting everything analytically. In particular, the 3-point functions I can't now get analytically because of this degeneracy. The degeneracy means that at the moment there is no answer to the unmixing problem of the degenerate operators. So the singlet, the singlet I think is fine probably, yeah. But for other, yeah, indeed, yeah. O2. The first case is twist 8020 representation. There are two operators there that have the same, the same naive dimension and the same anomalous dimension. Exactly. Yeah, no, you're absolutely. No, I did say in order to follow the same route that I've done so far, there's a problem. But you're entirely right. You don't need that. But you see, as I said, we found everything analytically, and therefore originally, and we kind of needed it. Well, we didn't try. We didn't try any other way, but we needed a very large number of terms to fit analytically. But now, anyway, the main point is now we don't need that because we have this formula of Zeeman and Thrin. They give us the double discontinuity of any correlator for free. So we don't really need any of that. But I mean, it's still an interesting problem to find the 3-point functions, but it's not really needed. So the double discontinuity at what do you mean at one loop? 1 over n to the 4th. Yeah, they give us this formula. So to any order. I mean, of course, it's tree-level data. It's the same data, but they actually yeah, exactly. They give us the formula directly, already summed up and everything. So somehow, because morally, it's because as we just heard, all the higher charges, at least at tree level, are induced from the 2222 case, and that is summarized by this formula. So I won't go into details of the formula, but these are all differential operators which are explicitly known, and this is a function which is explicitly known. So you have explicitly the log to the, if you want to do 1 over n to the 6 or whatever, you already have the triple discontinuity as well. Okay, so that's a big practical help. Now here I'm trying to draw something about below threshold data. So there's more data now that we can extract from previously known results that impact at one loop. And that's because of the following. So here I'm drawing, this is the twist, and I'm considering the spectrum of operators that you get from the OPE of OP1, OP2. And at leading order, you only get twists higher than P1 plus P2. But at order 1 over n squared, you also get operators of lower twist. And then similarly on the P3, P4 side, you only get twists higher than P3 plus P4, and then below that you only get operators of order 1 over n squared. So you can see actually that there's a few interesting things going on here. So first let's look at this below threshold. So for twists below the minimum of P1 plus P2 and P3 plus P4, at tree level I'm going to get for the first time an OPE coefficient of order 1 over n squared for some operators from the tree level case. And if I multiply those together, that's going to give me a prediction at order 1 over n to the 4th, purely of the rational term of your one loop correlation function. So similarly here in what we call the window, you have, first of all, you have some n to the 0 data from the P3, P4 side, but on the other side you get some 1 over n squared data, but also the anomalous dimension of order 1 over n squared. So that gives you a non-trivial piece of the log U answer at order 1 loop. And all this data is needed. If you just play the same game as before and try and write an ansatz using the double discontinuity, you find many unfixed coefficients. You need to also use this data to fix the coefficients. So this is what I was just trying to say, actually. So, so you get a prediction of a certain, not the whole log U sector by any means, just the low twist log U sector. So the twist in the window, W is the window. So twists in this sector, you get a prediction for the log U piece of the one loop result. Okay, this is because this is 1 over n squared, and this is 1 over n squared. So the whole thing is 1 over n to the 4th. And similarly, in the threshold part, so when tau is between 2a plus b plus 4 and here, just below that line, sorry, just below that line, the minimum of p1 plus p2 and p3 plus p4, then you get this prediction. Now, all of these things need to be unmixed, of course. Some of this has already been done. On this side, this C0 has already been unmixed, but you need to unmix the other stuff. So it's very intricate, but well, Hinek, Paul, and Francisco and Aprila in particular have been working very hard on all of this story. Now, the second problem is, well, okay, sorry. The second problem is that, in fact, if you take a minimal ansatz based on the double discontinuity, now what this means is that the double discontinuity has certain powers of x minus x bar, and it has certain poles in V as well that appear for the first time. It's natural to try and, take a minimal ansatz. You always want to take a minimal ansatz somehow to make life easier. If you take the minimal ansatz based on that, then you actually find it's inconsistent with the predictions I've just been talking about. Okay, so one solution is just to widen the ansatz, but in actual fact, that, well, to begin with, that's fine, but when you start looking at higher charges, it becomes too big that way. Now, there's this interesting feature which I'm not sure we really understand the meaning of this yet, but in fact, the most efficient solution is to consider two problems separately. First of all, take a generalized, what we call a generalized tree. So first of all, I'm going to give a new derivation. This is quite nice because you gave us two derivations of tree level. I'm going to give you a new derivation, which is very much after the fact. It very much uses the knowledge of the structure that you've already found. But in fact, if you take this ansatz, so again, it's the same story as before. It's polynomial times box, log u, log v, and polynomials, but with explicit powers of x minus x bar and v's in. Okay, so this is what you find if you look at your results. So now try and reproduce them by inputting that as an ansatz. So you input that as an ansatz, and you insist that it's first of all, it's consistent under crossing. Second of all, it's non-singular as x goes to x bar. And third of all, the key thing here is that you insist on cancellation of below threshold operators from free theory, at order 1 over n squared. Then this gives you an alternative derivation, if you like, of the tree. Well, it's not really, but I'm just saying we're taking a very specific ansatz here, so it's a more restricted ansatz. Okay, maybe we can discuss that. Let me go, because I mean the main point is not that this is supposed to be some new profound derivation of the thing. The main point is that now if I increase the ansatz by 1 over x minus x bar squared, so you see the only difference here is here I have a d1 minus 1, here I have a d1 plus 1, and so on and so forth. And do the following. I do the same as before, but now I can actually solve this problem and cancel all free theory operators for all n. In fact, you can take an arbitrary, like an abstract free theory with arbitrary coefficients, and you can always cancel all of the below threshold operators. So this gives you, if you like, some new tree-like functions that are linked to any free theory. Now, the strange thing is that we actually don't want to cancel these below threshold operators, because they are there at 1 over n to the fourth. They're missing at 1 over n squared. They are there at 1 over n to the fourth. However, it seems that if you do that, if you add the generalized tree to cancel the below threshold operators, then this minimal ansatz consistently gives you, the minimal ansatz itself consistently gives you the correct below threshold corrections. So it's fair to say, I don't think we really understand that, this is an experimentally achieved fact. But this is the most efficient way of doing things. You cancel using this generalized tree, and then you use the minimal ansatz, and that gives you the answer. Okay, so what can I say? I'd be interesting to discuss the meaning of that further. Okay. Now, there's another subtlety, which is the so-called semi-short sector, which again you don't see in the 2222 case. And there's a long story. There's a lot of arguments about these operators. But the basic point is that naively there's an ambiguity, because there are operators in short multiplets. If I take a particular short multiplet and add to it another short multiplet with twist 2 more and spin 1 less and some slightly different SU4 charges, then the two things together give you a long superblock. Actually, the full story with multiplets is a bit more complicated, because there's a diamond structure of recombination. But for the 4-point function blocks, then this is the story. Now we know that at weak coupling in n equals 4 super Young-Mills, this combination can take place. So the Konishi operator is a famous example of that. Konishi starts off in life in the free theory as a semi-short operator and a quarter BPOT operator. But they combine to become a long operator. And then, well, of course, if you're doing perturbative expansion, then it gets an anomalous dimension. But at strong coupling, it completely disappears from the spectrum because it's a string state. So there's a complicated story here. And in fact, it looks as if it's, first sight, it looks as if it's ambiguous. At second sight, because of this 1 over n squared feature, it looks like there's a way of always getting rid of them. But in actual fact, that's not the case. You cannot always remove the below threshold contributions. That's only true at 1 over n squared. But there is a way of correctly dealing with the semi-short operators. One can reconcile the ambiguity. And there's 2 ingredients for doing that. Okay, so the first ingredient is that there are no semi-short operators with twists greater than P1 plus P2. This is again coming from superconformal symmetry. So this, if you like, so there's a chain of, you've got 2 short operators that become a long. But there's a chain, because then it can combine with 2 more to become long. There's a whole chain of these semi-shorts. But it has an endpoint at the top, namely if my twist is P1 plus P2, then I can no longer combine upwards. So this gives us the following equation. So S here is the correct semi-short coefficient of the block expansion. A is the naive semi-short coefficient you get from free theory, and L is this long coefficient, which. So I'm just doing free theory analysis here and trying to separate out the genuine protected and the long stuff. So this is the long thing, which eventually that's going to go to 0 when we go to strong coupling. Okay, so this algorithm I'm giving here is recursive. So the fact that this has twist tau minus 2 means we've already found this at a previous stage in this recursive algorithm. So this gives me the correct data, semi-short data. Now the second key point is that we somehow have under control our double trace semi-short operators. By the way, I should say this is true. I can do this for double trace only. So again, it's only true at 1 over n to the 4th. there's going to be a more complicated story at higher orders. Okay, but at the level that we're looking at, these are the operators. They look similar to before. You can't have any box. As soon as you have a box, then your operator is long. And the twist has to be directly related to the SU4 quantum numbers in this way. Okay, so we know exactly how many semi-short operators there are. This is a key point, actually, which has been argued about in the past, but it's correct. I mean, the point is the semi-short operators are the ones built from the half BPS operators. Okay, so now what I can do is now I can consider a matrix of correlation functions. And this matrix is mu plus 1 by mu plus 1 matrix. When I say of correlation functions, I mean of the corresponding coefficients of the correlation functions. Now, the matrix, these are the components of the matrix. But the main point is that almost all of these correlation functions satisfy that P1R plus P2R, so that plus that, is equal to 2A plus B plus 2. So basically, we're in the situation we had before. So in other words, to cut a long story short, I've got a matrix. I've got a big matrix, all of which are known recursively from a previous stage. But the bottom corner of the matrix has my arbitrary PI, P1, P2, P3, P4 correlator. And so that's the unknown that I want to determine. But the claim is that M has 0 determinant, simply because it's a mu plus 1 by mu plus 1 matrix that is secretly C transpose, where C are both mu plus 1 by mu. So the matrix secretly has rank mu, and therefore the determinant is 0. It's a bit like a gram determinant, actually. In fact, it is a gram determinant, I think. So anyway, this gives you a way of computing these guys. Okay, now the main point here is that it's a complicated algorithm, but it can be done purely in free theory. And what's quite amazing is this fact at the bottom, that if we do this bootstrap that I've been talking about with a minimal ansatz and so on, it correctly gives results consistent with this semi-short prediction, which is completely different computations. And it's non-trivially consistent in the sense that it gives you, it gets the normalization right of the semi-short business as well. Okay, so that's where I think we are so far. Now, I don't have any time left, but of course you can extract data from the correlation functions. So you can extract the twist 4 data. Again, there's mixing problem to do. So from the 2222, you can only extract the twist 4 data because it's the only one that for which there's only one operator. But now we have a few more one-loop correlators. We can start doing the unmixing at the next level. And so here are the results that Hinek kindly produced for me recently. So here are the results for twist 6 unmixing. And they satisfy reciprocity, which is equivalent to this formula. And sorry, let me just say one thing. They're rational functions still, which maybe it's not surprising. I mean, we would have been surprised if they hadn't been rational. But Simon Karen Hewitt, of course, reinterprets that to mean there's some 10-dimensional symmetry. So we don't understand how the 10-dimensional symmetry goes down to 1 over n to the 4th, but there's at least hints that it's there in some way. Okay, so I will conclude. There's a long list of conclusions there, but okay. So obviously one would want to look for higher loops, maybe. Simplifying the results we already have. So there's this 8th order differential operator I haven't discussed very much, but it can be pulled out from the double discontinuity. And the question is, can we pull it out from the full function? It seems you can, but there's another leftover tree-like bit, which is different from the other tree-like bit. So, There's the melon space, of course. Fernando wrote a paper that recently converted this into melon space. There's a short-term goal that we have as an aim, if you like, which is to try and look at this degeneracy I mentioned. At twist date 020, there's a degeneracy. We would need all these correlators at one loop, and then we could try and answer the question as to lifting that degeneracy, which I think would be interesting. Because also the degeneracy is another prediction of the 10D, as far as I understand. So whether it lifts or not has some impact on the 10-dimensional symmetry. Of course, the string corrections, string loop corrections, and many people here have been looking at that. And then there's the Ema theory. I know you've heard talks about this previously. I guess the main sticking point is still the superblocks, but there is a nice story there. But again, well, that's still to look at. Thank you. Oh, okay, sorry.